Yeah, so we're going through in class this proof of the prime number theorem, which is quite nice because it's one of the only elementary proofs that it kind of involves everything we learn up to the end of high school. And we basically ran out of time in class, so I'm gonna look through the rest of this here. And basically all we have to go is the part that says now we write delta equals this, and it's actually only like a page left, which gets to the end of to here. And that's the end of the proof. Yeah, so if you don't follow this, you might have to review some of the earlier parts of the proof. But we're just gonna go from where our class is up to. So here, so delta equals this probably won't make sense till later, but it's nice to check at this point that it's bigger than alpha. So 3 over 2, alpha is bigger than alpha, and a1 is gonna be positive. Okay, so here, zeta to be any positive number, consider the behavior of v of eta. Okay, so v of eta in this interval, apparently it decreases steadily as eta increases, except that it's discontinuities where v of eta increases. So it's talking about, so the v is defined to be this this thing here. So it's e to the negative xc times the Chebyshev function of e to the xc minus 1, which is the sum of Mangold functions. And so I guess what it's saying is, because this is, of big O of, this is big O of e xc here. Wait, so okay, so maybe if you look at this one, it's more obvious what it's saying. So, oops. So you have this. So as xc increases here, the e to the minus xc is making it smaller and smaller. Okay, but every time you add something to the sum, it gets bigger. But it's like a discrete sum, so before anything gets added, it'll just be constant times this thing, which is getting smaller and smaller. So that's what decreasing steadily means. And then every time it gets to the next place where a new summand appears, it jumps up. And that's like a discontinuity. So, okay. So, either something evaluates to 0, or the v changes sign at most once. Okay, what does that mean? So I guess, I'm gonna draw on this. I can't draw at the moment. I draw on this. So it's like decreasing steadily, and then it jumps up. And then it decreases steadily, and then it jumps up. So if it's above 0 and doesn't hit 0 when on the way down, and then goes up, it's not going to hit 0. And then if it goes down again, it doesn't hit 0 and goes up, it's not going to hit 0. So in that case, it doesn't change sign at all. So what if it starts below 0? It could also be below 0, I guess, and then jump up. So that's the 0 line, let's say. And if it doesn't jump up to above 0, it's not going to change sign. But it could jump up to above 0, and then there's nothing that equals 0. And then that's a sign change. But then you're in the first situation where the only way to get across 0 is by the steady decrease instead of by the jumping. So on the way, if you're below 0, you could jump up above 0. So that's the one sign change that it's talking about. And if you're above 0, you can only decrease steadily down. You can't jump down, so it has to pass 0 if it changes the sign again. Okay, that's good. And so then I guess the calculation is in these cases. So in these intervals, so is it true for any interval? So either there's something where it goes to 0 or just, yeah, and there's lots of typos here as well. And then this is zeta. Zeta to zeta plus delta. Okay. Okay. So we're talking about this interval here, and we checked that it's greater than alpha, so this is something bigger, from zeta to something bigger. I guess it doesn't assume anything on the interval. So this is zeta to zeta plus delta. Okay, but I guess it's not talking about this interval more generally than it is, which is good because it could get a bit confusing. So here we're talking about zeta to zeta plus delta, and we're using this specific interval. So we're breaking it up into so this interval contains this interval. Okay. So if there's a value that gives you 0, yeah, so I guess that's good because we have a lemma here that we proved last time, that if you have a value that gives you 0, then the integral from 0 to alpha is bounded. And alpha is defined to be the lim sup of the absolute value of the v's. Okay, and then we actually did last time that alpha is less than or equal to beta, and we're assuming alpha is not equal to 0. And we're trying to get a contradiction. Okay. So, and if we show alpha equals 0, then we've effectively proven the theorem. Okay, so yeah, so if we have something that goes 0, we have this thing is bounded by half alpha squared plus big O of 1 on eta naught. So if we break it up from zeta to eta naught to eta naught plus alpha, so notice that's sort of from 0 to alpha. The length of the interval is alpha. And then here we have the rest, so eta naught plus alpha to zeta plus delta. So this thing here is a v of eta, but if you change the variable to v of eta plus eta naught, then it would start at 0 and go to alpha. So that's where the half alpha squared plus big O of eta naught inverse is. But big O of eta naught inverse is also little o. It's like it's dominated by little o of 1. So you can just include it in the little o of 1 term, and then alpha times, yeah, so this is just, I think, so the length of this integral is eta naught minus zeta. Yeah. So we're doing this thing where for an integral, if you have a bound for the integrand, the thing inside, then the whole thing is less than or equal to the length of the interval times the bound. So here we have the v is bounded by alpha plus little o of 1. And so the whole integral is just alpha plus little o of 1 times the length. That's what happens here as well. Okay. Yeah, so I guess the little o of 1 can be a bit confusing, because how does that come out of the integral? And but the point is, like, these both, so the o of 1 from each of those, just so all of the error terms come to the little o of 1 here. Okay. Yeah. Okay. Yep, so if you add all these together, so the eta naught cancels the eta naught, zeta cancels the zeta, you just get delta minus alpha. And the half alpha here becomes minus half alpha. It's a factor of alpha, so that's good. Yeah, so then you can write this as alpha prime times delta, where alpha prime is just this thing with delta pulled out of it. And alpha prime is less than, this should be alpha, because it's alpha times something less than 1. Okay. Okay, so in the case where it changes sign just once, so there's also the cases where it changes sign not at all. And so here's when it changes sign once at eta 1. Then this thing here. So the good thing about the sign change is you can assume the absolute value is not needed when it's plus, and when it's negative, you just make it negative. But I guess you can break it up, the integral, into the parts where it's consistently one sign. So it takes the same sign here, so the absolute value can go on the outside. And it takes another sign here, the absolute value can go on the outside. And when the absolute value is on the outside, we had this lemma, which showed that the whole thing's bounded by A1. So the whole thing's bounded by 2A1. And we should note that 2A1 is still less than alpha prime times delta, because delta, when delta is greater than, delta's it's delta times, wait, what am I saying here? Because the delta times 2 alpha times alpha is at least 2A1. So this is less than delta times alpha. Is it less than alpha prime times delta? Alpha prime is this. So you times this by delta. Yeah, so if you times this by delta, you get, this is half alpha squared. Right, it should be easy to check this. I'll check it. Okay, I'll come back to this a bit later, but let's see. Yeah, so it's bounded by 2a1. If it does not change sign at all, yep, so the absolute value just goes to the outside straight away. It's bounded by a1. Yep. Okay, so when you go from zeta to zeta plus delta, in the second case, you can break it up into these regions where this one is bounded by 2a1 and this other one, okay, so this is another one where it's this thing is alpha plus little o1 and this interval has length alpha, and I guess alpha times little o1 is still little o1. Okay, and then the alpha double prime delta is just dividing this by delta here. And remember delta was it was something on 2 alpha. So the alpha and so the 2 alpha times that to get you the alpha on the outside, and the 4a1 plus 2 alpha squared. And the something was 4a1 plus 3 alpha squared. See, 4a1 plus 3 alpha squared. You get this. And then top you can add alpha squared and minus alpha squared to get 1 minus, and then if it's just alpha squared, you can take an alpha out, divided by 2 to make it 2 alpha, and then you get delta again on the bottom. So this is exactly the same as alpha prime. So alpha double prime is the same as alpha prime. Okay, so it's saying in all the cases zeta to zeta plus delta, the integral is always less than or equal to alpha prime delta plus little o of 1. So that's the case here. We don't have to worry about this separately, they're all part of this case. Yeah. And that's the case here. Okay. Alright, almost there. This is the final part of the proof. So, yeah, little o1 just means it goes to 0. But sometimes it's confusing what variable goes to infinity, so in this case it's zeta. Okay. So these things are all sort of functions of zeta. Yeah, because if you have a constant times little o of 1, it doesn't change little o of 1. So here we might have needed the zetas to cancel. Because if the zetas don't cancel, you might get little o of zeta. Okay. Alright, so let M be the floor of C on delta. Okay, so yeah, maybe we should, yeah, the ultimate goal here is to prove that beta is less than alpha, and that's the final part of the theorem, and beta is defined to be the lim sup of this expression, so 1 on xc, integral 0 to xc, v of beta, this thing here. So we're at the home stretch, okay, so we're getting all these bounds for integrals of this thing with across these delta intervals, and we're trying to get it across a big interval using these little delta intervals. So let's see what happens. So from 0 to xc, you can break it up into all the deltas, as many deltas as you need until there's, so that essentially this is no longer, this interval is smaller than delta. Okay. And okay, we're saying that for each so for each integral across the length delta, it's alpha prime plus little o of 1. And there's m of those, so it's m times alpha prime delta plus m, capital M times little o of 1. Okay. And the big O of 1, I think that just comes from the last integral here. It's big O of 1. We have that here somewhere. I mean, well, that's with no absolute value sign. Here has absolute value sign. So it's a little interval. Okay, if it is true and it's equal to this, and when you divide by xc, you just get alpha prime plus little o of 1. It's getting really close. What's happening here? And so is this true for every interval of length delta? Zeta is arbitrary. Zeta is any positive number. Zeta is any positive number. So then that should work for all of these intervals here. And the little o of 1 is going to infinity as what goes to infinity? It's like 0 goes to, as zeta goes to infinity. But here the zeta is the you have m lots of O1s. I guess they go to infinity with xc. big O of 1 is just a constant. So the constant is supposed to come from this. Okay, and then xc, where is the xc? So xc is actually m delta plus this difference. So m delta is sort of like xc. And what's happening here? M delta, you have alpha prime xc plus alpha prime, and here it's xc. So m delta minus xc. So this thing here is less than 1. So minusing something less than 1 times alpha prime. Yeah, so if it's less than 1, it's like a constant. You could probably eat that up in the O of 1. Or in any case, that when you divide by the xc later, this will go to 0. So it'll be in part of the little O of 1. Okay, that's fine. What's going on with the little O of m plus the big O of 1? So little O of, okay, I should write this. So it's plus, so this thing equals alpha prime xc plus alpha prime delta m minus xc. Plus little O big M plus big O of 1. Okay. So we're trying to show that this stuff here is little O of xc. Yeah. So if we divide by xc, does it all go to 0? Okay. So if we divide by this by xc, so this thing is less than 1. So it does all go to 0. Yeah. This goes to 0. This is a constant, so that'll go to 0. And little O of m, well, m is xc on delta, so it's getting bigger and bigger with the xc. So let's see, how does this work? Little o, so we know little o over m. So when you divide that by m, it goes to 0. Okay. And now we're dividing it by xc, and xc is xc is bigger than m times delta. So this is less than small o of m on capital M times 1 on delta. And so then the delta is constant, so then that goes to 0 as well. Okay, I hope I did that part right, but like, okay, so that part's true if that goes to there. And then we're saying that capital M times little o of 1 is little o of 1, and then, so I guess we haven't fully checked that this thing is big O of 1. Okay, so why is that thing big O of 1? We know V is big O of 1, so the interval is less than 1, and the V is less than alpha plus little O of 1. So we want to get, do we want to get another alpha out? So alpha plus little o of 1 times 1. Like, does that work? So little o of 1 just goes with the little o of m. Yeah. The little o of, wait, so little o plus, we divide by m, that'll go to 0. Because this already gone to 0, so that can go with the little o of m. The alpha is just a constant. Wonder if I did that right. So I guess in the next step, when you divide by xc, these all go to 0 anyway. So, right. What's next? Then you have, okay, so now we have this thing here, 1 on c times this is less than or equal to alpha prime plus O1. You know? So beta is defined to be the lim sup of that. So if we take the lim sup of both sides, we get, so here the limit is just alpha prime. Okay, so the lim sup is equal to the limit. It's alpha prime. On the other side, the lim sup is beta. Okay. Then we get beta less than or equal to alpha prime. Okay, and we showed alpha prime is less than alpha. Which is less than alpha. Oh my gosh. So this is the end of this epic proof. So we assume that, so we showed before that alpha is less than or equal to beta, and that if we assume alpha is greater than 0 though, we get that alpha is greater than beta, so that's contradiction. So then alpha equals 0, and that proves the prime number theorem. Okay, as if alpha equals 0, let's see. Alpha is the lim sup of this V. And we had that if we can show V goes to 0, the limit of the V is 0. Yeah, I guess obviously like if it's positive, it's an absolute value. If the lim sup of the absolute value is 0, and the lim inf is probably 0 as well. And the limit's just 0. I think we went through this already though, so and then the limit's 0. So we're trying to show this. And this is x plus r, and r is the v on. R is v times e. Yep, so if the limit of v is 0, then so this means this divided by that has limit 1. So when you do this divided, you get 1 plus this divided by that, x, and that's just v. And so v goes to 0, then this goes to 1. And then we showed before that the prime number function thing is twiggle this over the log thing. So, oh my gosh, that's it. Finally, we did it.